creates two right angles and creates two congruent segments. And this is a really easy thing to show visually on how it all is developed and how it all works. For example, if I take segment AB and I say that segment CD is perpendicular to it, is a perpendicular bisector, excuse me. So if I say that segment CD is the perpendicular bisector of AB, that means we know that we have the two right angles that are created, and we also know that AD and BD have to be the same. So we can easily put away the book, make the right angles, and create the tick marks. Are we all right with that? That's nothing new. That's stuff that we've done before. If you think about it, we did all that on that progression sheet. But here we're not having to worry about writing it out in terms of a proof itself. All we're doing is we're writing it out in terms of how you can mark your diagram to show how what was created. Now, excuse me, if you got rambunctious here, how many more segments would you have to draw in to create a triangle? Two of them. One at AC and one at BC. You okay with that? Let's draw that. Now, at this point, you have a side and an angle. What can you say about CD? Reflexive, yeah. It's reflexive, isn't it? So if I draw that in, I say I have reflexive here. That means I have two triangles that are congruent because of what? Side, angle, side. I have two triangles that are congruent because of side, angle, side. Now, by knowing that I have two triangles here that are congruent, what can I say then about CA and CB? They're equal, right? What was that reason that we would say that after you had triangles congruent, what would you say next? Very good. Corresponding parts of the congruent triangles are congruent. So that means then, what kind of triangle did the perpendicular bisector create? No. Not necessarily. No. Yes, it made a right angle. But what kind of a triangle? It made an isosceles triangle. Because if you think about it, CA and CB, they're equidistant to the endpoints. When you're equidistant to something, that means you're equal. It means you're congruent. You have two congruent sides, therefore you've got an isosceles triangle. Now you said equilateral. Technically, yes, this could have become an equilateral, but an equilateral is more specific form of an isosceles. Just by saying isosceles is generic. That makes sense? So in this case, you create an equilateral triangle. Now, what happens here is that no matter where you put that point, even if I put C here, wouldn't it still be equidistant to here and here? Because this is still reflexive, isn't it? So what happens is, anytime that you are on a perpendicular bisector, no matter where you are, you're always, always, always going to be equidistant to the endpoints of the segment. Because you can always create side angle side. And that's kind of the trick on these things. There's a lot of subtleties within these new parts of triangles that allow us to do things from proofs and whatnot to show how other things happen. So, excuse me. So in this case, if you are on the perpendicular bisector, you are equidistant to the endpoints of the segment. Okay? And basically, the whole rationale, the whole reason that that happens is because of side angle side. Where you always get your sides from the bisector part, you always get the angles from the perpendicular part, so you have side angle, and then wherever you are on that perpendicular bisector, that always becomes the extra side because it's always going to be reflexive. So no matter what, you will always get side angle side with a perpendicular bisector. And that always then creates the parts going down to be congruent. Okay? It's one of those little nuances to awful things that you can do. When we used to teach isosceles and equilateral triangles for proofs, this is one of the things that we would actually prove via two-column proof. It's not real difficult to do, but as you can see, if you've got perpendicular, you're going to say you have right angles, then you say that they're congruent, then you say that you have segments that are congruent, then you have to say that you've got reflexive property, and so on and so on and so on. It just becomes a really long proof for something we can just use the definition of. Which basically is going to allow us to do, I don't know, a bunch of algebra. So I know it's been a while since we've actually had to math more in math as opposed to thinking more in math. So make sure if you've been slacking and not bringing a calculator, bring a calculator. Okay? You need to have one pretty much from here on out. So let me show you what I'm talking about with this. Did all this. We're going to be able to do a whole bunch of algebra. Okay. Don't sound too excited. So we'll be able to do a whole bunch of algebra with this stuff now. And it's like I was saying earlier, there's a lot of vocabulary in this chapter where if you're not careful with it, you might mix something up. It's not that the math that we're going to do is going to be horribly difficult, but what's happening is that there's going to be a lot of different terms that we're going to use, so you have to be cautious in what they're talking about. Let's see. We'll talk about it. What happens here is that in a triangle, you can have three midsegments, right? Technically, you could also have three perpendicular bisectors. So they don't always necessarily have to go through a vertex. They're just drawn out differently. So we're going to get to problems like this here a little bit later. Now, is BD in the perpendicular bisector of AC? Yes. No. Yes. It is, because it's perpendicular and it's got tick marks for the bisectors. So, that means algebraically, so you set it up algebraically to find x, which is 4x equals 6x minus 10. And then you're back to a problem of variables on both sides. Now, normally I would always say pick on the little guy, but if I do that, I wind up with a 0 on one side, which means I have to move a 10 around. Yeah, in this case, sometimes it's okay to work the other direction. Just remember you have to deal with negatives. So if you subtract the 6x, you get negative 2x is negative 10. Therefore, x is how much? 5. Okay. Now, what I'm always going to be an advocate of doing, besides staying off phones and reading books and other things while we're trying to do math stuff right now, is to always check our work. It only takes a second to do that. Put it away. Thank you. It only takes a second to go back to double check to make sure you're not screwing up, because it's so easy to do these algebra problems and just make a dumb mistake. So check it. What's 4 times 5? 20. Okay. What's 6 times 5? Subtract 10. What do you get? Does 20 equal 20? Yes, so you didn't screw up. It's one of those things that you guys were taught how to do a long, long time ago that they kind of stopped enforcing. Remember in algebra, a lot of times it said, show your work and check your answers. Notice how it doesn't say that very often anymore? They're kind of letting you guys have a little bit more leeway with your work. But as you can see, it only takes a couple of seconds to check it. Check it. Because it's so easy to make a dumb mistake. Okay? It's one of those things. Same thing here. Could you figure this one out to solve for the side lengths? All right, solve for the side lengths, please. So algebraically again, you know they have to be equal because QS is the perpendicular bisector. Means they have to be equidistant. Variables on both sides. Take on the little guy again. Is it okay if I do them both at the same time? Move the 3, move the 7? Yeah. Subtract 3x, add 7. 6. So we get 3, 4x. And then once again, always substitute back in. 3 times 3 is. Subtract 1, you get. And then 5 times 3 is. Subtract 7, and you get. It only, yes, sir. Yeah. Again, it only takes a second to do it. It doesn't hurt any. Which gets us to be able to then switch and talk about angle bisectors. What do you think angle bisectors do? I'm sure it sounds like they bisect angles. Okay. I'm going to go out on a limb on this one. So angle bisectors. Angle bisectors bisect angles. When you bisect an angle, what's created? 2 congruent angles. Good. So angle bisectors bisect angles. You create 2 congruent angles. Here and here. Go right with that. That's just straight definitions from things that we've known, things that we've done in the past. It isn't anything stretch at a stretch of what we already know. Right. So you get an angle bisector. Now, here's what happens with these things. What I want you to do is think about how you use a tape measure. You want to use a tape measure to measure something. How do you measure? You measure it on an angle, you measure it straight. You measure it straight because the shortest distance between 2 points is always a straight line. And it's always the shortest distance between 2 points when you are perpendicular or something. So if I wanted to measure from here to the door, I'm not going to walk on an angle to the door. I'm going to walk straight to the door so that way I run into it at a 90-degree angle. That's why we say things are square. Remember, we talked about that, right? When you measure stuff out, check to see if things are square. That's what you're doing. So if you pick a point on here and you draw to the side, the shortest distance would have to be a right angle. You okay with that? So here, what would this be then? It's reflexive, isn't it? So don't you wind up with two congruent triangles here? Because of angle, angle, side. Because the side's not between them. If you put a point on an angle bisector, that point, when you measure to the side of the angle, is always going to be perpendicular to it, because that's how you measure distance. Which then means that no matter where you place it on the angle bisector, it's always going to be the same distance from that point to the vertex. That's why we say it's always going to have a reflexive part to it, which always creates angle, angle, side. Which then means that if you're on the angle bisector, you will always be equidistant to the sides. And that's what I was getting. So if you're on an angle bisector, you are perpendicular and equidistant to the sides. Always, because you can do and show that you have angle, angle, side, because of that reflexive piece. Again, it's not something I'm going to have you guys write out in terms of a two-column proof or anything like that. You don't have to worry about those. But I wanted to show you why does this stuff work, and it always stems back from the ideas of working with congruent triangles. If you're able to create congruent triangles, there's so many things that you can show off of them, and this happens to be one. Not so bad? Which means, again, what do you think we'll be doing? More algebra. Okay, we'll do more algebra. For an example, something like this. I guess I can do that while I draw this up. Well, is R on the angle bisector? Yeah, because it shows it. You've got the congruency marks and you've got the right angles. Which means RM and RP have to be equal, have to be the same. Which means, what do you do now? You map it, right? Algebra. Super fast algebra with these things. There's really not a lot of craziness here. Gives you both segments are going to be equal to how much then, guys? 35. Both 35. Again, just take a second to check it out. 7 times 5 is 35. 2 times 5 is 10. 10 and 25 happens to be also 35. So it's not so. The weirdness with this stuff really does become when we start talking about all the different things that happen interior to the triangle. What happens in here? You get all these different segments that occur. You get these points where all these things meet. and they're called points of concurrency. We talk about that. I think we won't talk about that until after the quiz. I don't think they define it in 5.3. I don't remember. This book is weird. They've set up a lot of this stuff. We'll see how it goes. Try another one. Oh, algebra skills after a bunch of days off. Whole bunch of algebra to see if you remember how to algebra. After not algebra in the past 5 days. You guys get 3 for X, I'm hoping. When he subs you back in, you're getting 18 and 3, 21, 12 and 9, 21. I always check it just to be safe, because you don't want to do a dumb thing. Because there's a lot of times people do 2x equals 6, they'll say it's 4, because they'll accidentally think it's so. They'll do a dumb thing and subtract it instead of divide it. So don't do a dumb thing. That way you can catch yourself from screwing up. And that leads us to what happens when you get the big picture with these. And that's kind of like the goofiest of all of them. I apologize. I was telling the last classes, I completely brain farted and forgot to make a photocopy of this. That way you guys get a better picture of it. But take a second and do your best to draw this out. And what I want to do is kind of explain what happens when you have all of these in one picture. Blow this up a little bit. Okay. That's an N. So in this big picture here, what we wind up with is all of those dotted lines working outward. Those are all perpendicular bisectors. Okay. So take a second to try to draw this one out, because with just this little bit of information, you're going to be able to solve for every single segment that's in the triangle itself for all the parts. So take a couple minutes and try that. Like I said, I'm sorry I didn't have a free run for you, but take a minute or so and draw it out. Film why it's not all walking through what actually occurs. It's pretty easy to show. Now, as you're going through this one, draw this out, draw in what you know. You know that OQ is perpendicular to MN. So as you're going through it, put in your right angles. You also know that MQ and QN have to be the same. So that has to be 20. Very good. Same thing going around the other side. You know that that's a perpendicular bisector, which makes this right angles, which then makes these two guys the same, which means PR is 6. Again, we're just using the definitions going around. Hey, look, another right angles, or sets of right angles, which makes this 2. Okay. We're getting there. We're getting there. Now, if I look at this, if you look at this carefully, you might note well, I don't know if you'll notice this, but see how you wind up with 3 sets of different congruent triangles? You wind up with 3 sets of congruent triangles because watch what happens. This point here is on the perpendicular bisector for all 3 of those sets of triangles, which creates side angle side for all of them, which means that if this is 26.8, what's this? Which means this is 26.8. You okay with that? But it isn't, because remember, what's happening here is that O is on the perpendicular bisector for all 3 of those parts. If you're on the perpendicular bisector, you're always equidistant to the endpoints. So if one of them is 26.8, the other one has to be 26.8. Okay? That means then you have just the dotted lines left to figure out. Well, if you look at it and you redraw it out, if I just draw out M, Q, O, and I know that that's 20, that's a right angle, and that's 26.8, what is out there that allows me to work with right triangles to find this in side lengths? Okay. The big guy? What's the big guy? The A, B's, and the C's, which is the Pythagorean theorem. Again, you're using the Pythagorean theorem. Now, remember, it's not something that we actually have defined yet in this class, but it's something that every single one of you guys have done. Now, one of the things the only thing you have to worry about with the Pythagorean theorem is which of the segments is the hypotenuse. Which one is always the hypotenuse? Yeah, the one across from the right angle. It's C in this case. But remember, it's always going to be the one that's across from the right angle because it has to be the longest segment. So if I'm going to solve this out, you wind up with this. 20 squared plus B squared is 26.8 squared. We okay with that? Now, without pressing any buttons to start with, does everybody agree that I'm going to have to subtract the 20 squared over to the other side? At some point in time, we'll have to subtract it over. So we're going to get B squared would equal 26.8 squared minus 20 squared. Now, I want to start to show you guys how do you use your calculator with the answer function on it. Okay. On your calculators, it doesn't matter which one you have. If you've got some Texas Instrument one, you're going to have an answer button on there. That answer button is above, well, if you get second, the negative button. Okay? And the negative button for most of these are all that bottom right-hand corner-ish area. So here's what you would do. You would type in the calculator this, 26.8 squared, subtract 20 squared, and hit enter. And it gives you 318 and change. That equals B squared, which means to get B by itself, what would you have to do to that? It's square root. So without having to rewrite it all out, just use the calculator to help you get there. second square root. Most of you guys have to hit the second button to get to the square root function. It's like the superscript on the calculator is by the squared. And now hit second answer. And what it does is that it's going to use that last bit of info you hit enter for. So a minute ago we hit enter to get 318 and change. It's using that stored information, and now hit enter, and there's your answer. The square root of 318.24 is 17. I always round to 2 decimal places. So how do I round that to 2 decimal places? 17.839 rounds to 17.8. And that'll get you one of those segments. So you're going to start to see that we're going to mix up a little bit. What I say was 17.84. And I can do the same thing for finding this one. 22 squared plus something squared is 26.8. And just move it around again. And you use that answer button. That answer button helps you second square root of my answer. If I round that to 2 decimal places, 13.3049 becomes 13.30, so just 13.3. I said, what's that? Yeah, you can. That's what I was saying, is that you can figure out all segments then if you know just that little bit. So I gave you what, 13 point, I'm sorry, it wasn't 13, it was 15, wasn't it? 15.3, sorry, I don't know why I said 13. And then you can do that again to figure out what OR is. By doing the 26.8 squared, subtract 26 squared. Yeah, so what happens, guys, is we get into this further and further. Each of these types of problems we talk about are going to have different rules for working with big picture problems. Perpendicular bisectors are pretty easy because really all you're going to wind up working with is Pythagorean theorem. And you'll be able to figure out all the parts inside something like that by doing Pythagorean theorem a few times. Again, it's not really difficult to do, and it's something that we're hoping that you have recalled, that you paid attention to one math class at some point in time. They talked about this before, because Lord knows I never taught you how to add and subtract, but I still assume that you've seen it, so you have to know how to do it. So it's kind of the same idea, where we know that you've seen some material, so we just build off. Okay. That's all I had. It's not 296. We'll work through those. Okay? Yeah, that's super easy. I have not. Yeah, there's a strong secondary market for black pencil bags. People like that. You're back.